Hello, Alex Cole here from BobCAD-CAM. In this video, what I'd like to talk about is a commonly misunderstood or not understood function for 5-axis machines. It's called TCP. There's other names for it, RTCP, TCPC, and things like that. It stands for Tool Center Point Control, and it's an add-on function to a 5-axis machine to simplify programming, and it alters the coordinates because the controller on the machine has the kinematics of that 4th and 5th axis assembly, and it's able to do some of the math to track that head when you're rotating things in 5-axis. So to understand what TCP does, what I would first like to look at is just some simple rotations of a 5-axis machine and what they look like. So on the screen, what I have is a head 5-axis. I just have the column and the two rotaries here. So we have a rotary that rotates around the C. We have a rotary that rotates around the A axis. So if you walk up to your 5-axis machine and you just jog, in this case, the A axis, we're going to see this tool is swinging left and right, and that is what you would expect to see with normal rotation on a 5-axis head machine. This does also apply to table machines as well. So when you set up your work offset and when you set up your tool offset, you're effectively defining the 0 point on your machine, where that program 0 is and where the tip of that tool is, so that whatever coordinate you command the machine to go to, when it's like a 3-axis machine or in a 3-axis mode, the tip of that tool goes to that coordinate that you've entered. With a 5-axis machine, the exact same thing happens. In this case, with the 4th and 5th axis both sitting at 0, the tool is straight up and down, and that point is right here at the tip of that tool. So when you rotate, however, without any special functions turned on, what happens is that tool swings away from that point, but the controller doesn't know that. So when you're commanding positions to go to, the machine simply takes that point that's right in line with where the tip of the tool is when everything's at 0. It takes that point to the location that you've commanded. So with the TCP function, when you turn on the TCP function, I've created a simple little program that emulates kind of the motion that you see when TCP is enabled. And if I step through this program, what we see is that the tip of the tool stays still. Basically, the machine will rotate that entire machine to where the tip of the tool is staying at that commanded point, even though you've only commanded a rotation move. In this case, if we commanded A45, the machine would move X and Z and A to keep the tip of the tool at the spot that it was sitting at, but yet all those other components would move in conjunction, in coordinated motion, so that everything is just rotating about that point. So what that means, as far as the G-code program goes, is that your points, or the positions that you output to the NC file, are all relative to that kind of location there at the part. So let's look at another file here and see what this looks like in the code and what effects we actually have without having TCP turned on, and the way that point gets output. So to illustrate this, I have a toolpath. If I go to a front view here, I've created two different drilling operations, one that's drilling from the top plane, and it drills right to 0 and then stops. And then I have one that drills from the right plane, and it's drilling on the right side right to 0, and then it stops. So if we post this code out and we take a look at that G code, what we can see is that our initial top operation is just like a 3-axis operation would look, and everything is normal. So we're at XY 0, Z 1 inch above the part, and then we come down and we drill right to XYZ 0, and everything looks normal. But when we come to drill from the right side, we can see our rotation angles for this machine, but our x coordinate, instead of being at x0, we can see that we're shifted way over 17 inches, in fact, over. And the reason for that is because of the actual pivot distance on a machine. So I've pulled up an image here of a head-head 5-axis assembly, although again this same thing applies to table based machines. But what we have is we have 3 different dimensions that come into account when we're not running with TCP, and that is the distance A, which is your tool protrusion length, distance B, which is your holder length, and distance C, which is the distance from the face of the spindle to the center of the rotation axis on this assembly. Now, there can also be an additional rotation or a distance if the first rotary center line is not perfectly lined up with the second. Then there would be an additional dimension there that would need to be compensated for as this head starts to rotate. Now, the CAD-CAM software will do this automatically, and you'll hear me refer to this combination of all of these distances I refer to as a pivot length or an overall gauge length. And so based on your machine and based on the setup that you have on your machine's physical components, that will determine where these positions will be output. So if we launch simulation in this file, I gotta close it over here first before we can launch it in this file. Yes. Okay. And if we launch simulation in this particular file, just one moment here. What we'll see is, looking at this toolpath from the front view, so our tool is going to come down and drill to 0. But what I want us to pay attention to is the centerline axis on this component is going to have to change, and we've had to drop this head down. Now remember, we talked about that programming point. As far as the controller knows, everything is set up the way that it was as if this assembly was vertical. So the point that's actually output in the NC program is down below the spindle in like as if this was vertical at this point. So if I actually rotate this to 0, the point that's being output in the program is the location right here at the tip of our tool. However, in reality, the rotary axis has been rotated, and so we're compensating for this in the numbers. So we can see our X is over 17 inches, and then as we step to actually begin this drilling, so now we should be touching right at 0, which is our drill location, and we can see that we're actually moving in X to drill this, and our Z is at negative 15 inches, 0.8583. And that 15.8583 is the combined length of our tool and our holder and the face of the spindle to the center of rotation. And we can actually see that in the machine definition for the software. So if I open this particular machine, which is the BC head, and we go into this machine definition, we can see that 13.8583 is the value that was entered into the system for the pivot length or face of the spindle to the center of rotation. And then that additional 2 inches is our tool protrusion and our holder. So that's actually where those numbers are coming from. And if those numbers aren't configured properly, then your machine is not going to be, operating in the correct locations. So the CAD-CAM system takes care of all of this for you. Those numbers have to be very accurate to what you're running on the machine, or else this tool will not physically be in the correct location on your part. So what does TCP do for us? So as we see in this file, when TCP is rotating that tool, it's actually keeping that program point right at where the tool was commanded to go is what is maintained, and it stays there because the controller knows those distances. So it knows the length of your tool. It knows the length from the face of the spindle to the center of rotation. It knows if there's a shift or an offset. So the controller itself is actually able to compensate for those. And what that means for you is that when you're running a program with TCP, if you break a tool and you need to use a new tool, you go set it up in a holder, and the length of that tool is now different, then you will not have to generate a different NC file to be able to run that tool on your machine. However, if you don't have TCP, then you would actually have to generate a whole new NC program to be able to run on the machine, because those distances have changed. And it's not the pivot distance, like the distance from center line to the face of the spindle, that's going to change, but the tool length from the face of the spindle to the tip of your tool is going to change unless you have some very accurate method of setting up tools. So let's look at the actual code for a program that is TCP and see what the differences are. So these right now this code has been output without TCP. So we can see that these X values are shifted, the Z value is shifted down for this example. So I'm going to go in, and I have turned off TCP on this multi-axis posting page, but if I turn my machine settings back on, this machine does support TCP, so when I use the machine settings, it's going to revert back to TCP, and I post the same program out. What we'll see is our top program is actually being output with XYZ0, just like it was before, because we have not rotated. The TCP function is going to, if we look at our X's, we have an X value of 2, and then we have this X value of 25, or 0.25, excuse me, and then we actually move to X0. So these coordinates are very easy to understand because they're exactly what we're thinking about, as we can see here on the screen. We start at 2 inches out, we move up to 1/4 inch, we move up to the 150 thousandths away, and then we drill down to 0. So TCP allows these coordinates to be easier to understand as an operator, and they also allow us, if this tool were to break and we needed to change that tool and it ended up being a different length, we can still run this TCP program. So hopefully this helps kind of understand a little bit about how TCP affects the coordinates and what that motion difference looks like on the machine. And there's definitely more information and more examples that I can show of what TCP does. This is just kind of an initial intro, and maybe I'll make some additional topics if you guys request. I can make some additional topics about TCP and we can dig into this a little bit further. All right, well, thanks for now.